All right, for this next problem, now we're dealing with only a two-step reaction scheme. And before I go into this, I actually recorded the last one first. I have it up here. I want to say one thing really quick about alcohol activation, just to kind of clarify why we're introducing these new reagents and like why we can't just do the whole like acidic H2SO4 thing that we did in office hours the other day. So the whole idea, it really is because we could technically use H2SO4 for this step one, but as we know, if we protonate this and it's at a secondary electrophile, usually we only see things leave when they're at a tertiary alpha carbon. In this case, this whole water situation is just such a good leaving group. It's kind of just an exception that it will also leave at a secondary carbon. So this whole thing would leave, and we'd be left with a carbocation. I'm actually going to change this too to kind of emphasize the point I'm going to try to make. So anyway, if I am at a secondary electrophile here, I could kind of look around and see that, okay, I have a primary carbon here, but to my left of this central carbon, I have a tertiary carbon. So when I'm trying to activate this alcohol and let it leave like I did here, I am going to end up getting this carbocation that could ultimately end up shifting to this spot, and I will end up getting something that looks completely different from what I started with. Basically, what I'm trying to say is my reactive position went from this second to last carbon here to this third to last carbon here. And the reason sometimes we don't want this is because let's say I had, for example, like a problem like this. I'm going to use the exact same molecule that I just drew. Let's say I had like a problem like this. We go from like an alcohol here, and then let's say like she made, on an exam or something, the product look like this. So you might think, okay, I'm going to follow this whole like H2SO4 step where the H2SO4 would protonate this, it would leave as a really good leaving group, and now I'm like making this carbocation. But this carbocation is prone, like any other carbocation, it's prone to shifting, which is what we did. But now see how this carbocation is at a completely different spot than where we see this bromine end up attaching to. So we know that we can't end up making carbocation because my product, if I added like a Br minus in here, I'd end up getting this. And these two things obviously do not look the same. So the whole reason, basically, if this doesn't make sense, really, that's okay. We're going to do this more next week. And obviously, like, she'll talk about it in class more this week. But the reason we introduced this whole new alcohol activation reagent list is to specifically avoid carbocations. That is, like, the reason we're using these new reagents. I didn't say that in the last video. I just wanted to clarify that a little bit more. Like I said, we'll end up talking about it more. I know it's like a new concept, so that's basically the reason. Just avoiding those carbocations that we sometimes don't want based on where we see this like reactive spot end up. Looking at this, it's a two-step mechanism. We obviously see that the intermediate is not given to us. We have to get there ourselves. And also, unlike that last problem, we aren't given any of the reagents that could possibly be over these arrows here. So we're going to just have to, again, use what we know and just identify what's given to us. So I'm going to go ahead and do that. I guess I'll just start on the left just to see the differences between here and what we end up with. So again, I'm going to label the substitution of my alpha carbon here. So this alpha carbon is primary. We're just connected to one other carbon there. I'm going to say primary, and then it's also good to get in the habit of saying unhindered versus hindered for primary. So if that's our alpha carbon, I'm also going to look at the beta carbon. We have no like branches coming off of this. It's just one linear chain here. So I know I am going to be unhindered. So primary unhindered. I'll abbreviate it. So now that we have that done, I'm also going to look here really quick. And it looks like our alpha carbon, this new nucleophile that we'll end up dealing with later, is also at that same first carbon here. It's still primary, still unhindered. So that's just something we could look at to start with, just kind of identifying the things we know. Even if they won't end up helping us, it's just good to list everything out to see how it all connects together. So now that I have done that, So I'm noticing that these stereocenters here are also dial turned around this bond here between the alpha and beta carbon. We kind of just did like a little spin around that. So that's something we need to take into account too, just because it will help us kind of see if our stereocenter switched or not. Yes, like they're still properly wedged and dashed like they are in the starting material, but they're pointing in different directions. We're not going to really be able to see if anything switched or not, given this weird like 3D view of these molecules. So what I'm going to do right off the bat is try to make this look like something I could work with more. And what I mean by that is I can see right now that my OH here is in the plane up while my N3 here is in the plane down. I want to get these to point in the same direction and be in the same plane so I can properly compare the stereocenter and see if anything possibly switched or not. And what I'm saying will make more sense when I do it. Another thing too is the reason I highlighted the OH and N3 is because I know the OH on the left side, my starting material, is a really good candidate for, like activating into a good leaving group or something like that. It's just most likely going to be my reactive spot in my molecule. And the N3 is obviously something we don't see in the starting material. So this N3 here is most likely something new we added. So I know that's the spot we're going to be dealing with. So I want to try to get those pointing the same direction so I could compare how the entire like deuterium and H changed, or if they even did for that matter. So you can really redraw this any way you want. I'm just going to go ahead and make the N3 on my right-hand side point in the same direction as my OH. So what I mean by that is, like right now, I'm going to do like a quick Newman projection for this actually. I wasn't planning on doing that, but I feel like it'll make this clearer. So if I really quick draw like a Newman projection for this molecule, and also my eye is going to be here, looking down this way. I won't draw anything on the beta carbon here in the back. I'm just focusing right now on this alpha, just to kind of get us oriented. So if I do this, that's my back beta carbon. I won't be drawing stuff off of that. And here is my alpha carbon. I'll label it too. So if I want to draw my OH, deuterium, and hydrogen coming off of this, I know right now that my OH is in the plane, and if I kind of think of like some sort of horizontal line splitting my top from my top of my molecule from the bottom of the molecule, that horizontal line in my molecule is right here. So I have my top up here above that line and the bottom below the dotted line, and that directly correlates to these two sides of this Newman projection. So my OH is above that dotted line. It's pointing upward. I'm going to then draw it coming out directly up like this. If I imagine grabbing the bond between this alpha and beta carbon here and kind of rotate, I know I can't do this on the page in 2D, but rotating it so the alpha carbon here faces me, you can kind of see how the deuterium right now, pointing out of the page, would be pointing to the right if I turned this whole bond toward me so that the alpha's in the front and the beta carbon is like back behind me, or facing away from me, I should say. So again, this is kind of just like using what we know before about Newman projections. You don't need to do this for this, but it could kind of help you to see what's going on. So I'm going to draw the deuterium facing to the right, and my H is going to be on the left in that dash side. So now I want to try to get this so the OH and the N3 are in the same exact spot. So if I draw out my Newman projection for this product, looking down the exact same way as before, I'm going to do the exact same thing. So my N3 now, instead of pointing up above this horizontal, it's going to be pointing below. Again, you don't need to do the dotted line thing. I think it just makes it, you could orient yourself better sometimes, but my N3 pointing down. And then my H, again, if I turn this bond between the alpha beta toward me so that the alpha is pointing directly at my face, the H would be facing to the left, and the deuterium would be pointing to the right. So now I want to get this so that the N3 right here is also pointing up, like my OH on the left. So I'm going to do, it looks like it's just going to be a 180-degree turn to get it from this pointing down to directly being 180 across, pointing up. So if I do that, I'll redraw what I end up getting. The N3 pointing directly up now, it's going to be right here in that spot. So I'll draw that in. The H now is also going to go 180 degrees around and point right out here. So I'll draw that in my new Newman projection. And then again, the deuterium will also turn around that 180 degrees and be pointing directly across from where it originally was. So I'll do that as well. So when we started doing this, I didn't write this down, but the dash side is here on the left and the wedge is on the right for both of these Newman projections. So when I try to now redraw this final product in this new conformation, I will end up getting the N3 pointing straight up as before in the plane. I will end up getting my deuterium now. We know it's going to be pointing downward because it's below this horizontal line here. I know we know how to do these, but I just want to explain every single little thing. So also, it's on the dashed side of this Newman projection. So it'll be pointing downward, but be dashed. So I'll draw that in as well. All right, so we got the deuterium done here. We did the N3 pointing straight up, and now we're looking at this wedge side here. And it looks like my H will be pointing down wedged. Now, the whole reason we did this, even if it seems kind of unnecessary, I just wanted to go ahead and do this to compare what the deuterium and H are doing in between the starting material and final product. So you can kind of see right now, it looks like they switched places. That signifies ultimately an inversion occurred. So between this starting material and this final product, because these switched, I know an inversion must have happened. So I am going to just kind of like take note about this. So I'll say like inversion overall. And then another thing too is you can kind of see why we have to do this whole like flipping of the Newman projection situation, because on this left side the deuterium is wedged, and in this final product that we're given it is also wedged. but they're not pointing in the same direction. This is down and this one's up. So we're not really given a proper 3D orientation to fully compare them in the right way. The fact that we have inversion overall is kind of hinting to me that one of these steps must have been inversion to do that inversion. But then the other one, if I invert something and I want to keep it that way, I just want to keep this overall inversion, should I invert it again? Or should I retain my stereocenter and not touch the inversion I just completed? The answer would be just to retain that first inversion by your second step being like a retention step. This could also be the opposite, where let's say like I retain the stereocenter here, I don't switch anything around, then my second step would be inversion. So ultimately, overall, when you consider these two things, you would, in this case, switch something, keep it switched, or you would keep your starting material the same and then switch it, and ultimately, overall then, you get an inversion that occurred. If I'm going to now look at this new, this new orientation of this final product that I made, I am going to kind of just identify what this N3 that we added is and like what's the deal with it. If I am looking at this new N3 that we added, this is going to again come into identifying what type of nucleophile it is and determining the mechanism that likely occurred. So N3, this is going to be a really weird one. That is our molecule that looks like this. Kind of looks like there's a lot going on there, but this is one of our nucleophiles with resonance. This would end up being considered a good nucleophile weak base, just because of that resonance. I think I have it somewhere in here. I did not write it in here, but it would definitely be like in this lower left box down here. Specifically through resonance and conjugation that this charge would be delocalized through. Anyway, so we know this would be a good nucleophile because of this negative charge, lone pair. But this resonance through here, all this like flipping of these double bonds in lone pairs, and that of course would like flip back and forth, we'd consider this a weak base. So again, if I have a good nucleophile weak base and my intermediate, I know we didn't draw it yet, but our intermediate is most likely also going to be primary unhindered. We're not changing anything about that between the starting material and final product. If I pair a good nucleophile weak base plus something that is primary unhindered, the mechanism I'm going to overall get from this is SN2. And just as before in the last problem I did, what do we know about SN2? SN2, the main characteristic that's going to come with this mechanism is going to be inversion at the alpha carbon, or stereocenter we're dealing with. So, the fact that this step to get this N3 attached to this alpha carbon here would allow us to do this inversion that we obviously see occurred between the starting material and final product, based on the fact that this DNH switched their places. This is a good sign that we're on the right track. We've identified what N3 even is in the first place, the fact that it's a good nucleophile weak base. We recognize that when we combine it with some primary unhindered intermediate, we're going to get SN2, which would lead to our inversion. So this is a really good sign that our step 2 was this N3 nucleophile, which would lead to SN2, and we would get that inversion that we need. So now that we've done that, I know that because, like I said, we did inversion overall. So if we have 2 steps, I know that's probably going to be the only inversion step that we had. So this second step here, or this first step here, the second one we're about to do, is going to probably have to be retention. If I did 2 inversions, let's say now that we're like looking at this first step here, if I did an inversion, I'd invert, get something that looks like my final product, and then invert again with this N3. That would just leave me with something I started with. So instead of, for example, the final product looking like this, I'd instead get something like this. The deuterium and H would have not switched places like we wanted them to if I did 2 inversions. It would just flip directly back to what we started with. I always think of it as like 2 negatives make a positive. So 2 of the same thing lead you to what you originally started with. Again, this is something we just did or learned in class. So if it doesn't fully register, it's okay because we're going to do more practice with it. But that's just kind of another key that made me think, okay, this must be the only inversion step here. So we've got that dealt with. We're basically done with that. Now again, we just have to think about what step 1 could have been. So if I know this must be retention, just so I can have some intermediate that will allow me to do an inversion with the N3 that I know I need because I see it in my final product, and still get this molecule, that's going to be something that can activate an alcohol into a good leaving group. Because right now, again, we're dealing with a terrible leaving group here. And if we want to do this SN2 step we see, we know that we need a good leaving group. So this A intermediate must have that good leaving group on it. So what we can do to go from a terrible leaving group to a good leaving group that we know we need in one step. I'm going to write that too right here. So A must have a good leaving group. Is this alcohol activation. And because we know it's going to be retention, this is going to be very similar as before. It's going to be any alcohol activation reagent that does retention. So it can be any of these 3 here. Obviously it's going to depend on what the answer options say, so we'll scroll down to that really quick. So we know, we identified actually, I'll fill this in really quick. We know this is going to be an N3 molecule. And I also know that this part 1 of 3 must be some sort of retention alcohol activation. Obviously this is going to be just a salt. That won't do anything in solution. That Cl won't be able to attack the OH and make it leave because OH is such a bad leaving group. We know we need to activate the alcohol into something that can leave first before we deal with any SN2 type of mechanism. We know it can't be this because this does inversion. NaOH, again, would not do anything. It would probably just deprotonate this H and nothing else would happen. So that leaves me with TSCl and pyridine. Yeah, so this toluene sulfonyl chloride is just TSCl. So I know that this last option would be my answer. So I'd be good with part 1 and 3. The last thing we just need to do now is, I'm going to write that as well. Alcohol activation. This lets us install a good leaving group. And we know we need that good leaving group, because to do SN2 in the second step with N3, SN2, one of its requirements is to have something that can leave when we do that concerted mechanism. So again, all this is like a puzzle. It all kind of just comes together slowly like that. But the last thing, again, now we're just drawing our molecule A. So what I am going to do is redraw like the basic skeleton of what I have for my starting material. I'll go like this. When I use TSCl and pyridine, my good leaving group I attach is ultimately going to be OTS. And now we have to think, when we draw the deuterium and H we see here, are those going to be in the same spot or switched? Well, if we have to do retention and TSCl is one of our retention reagents for alcohol activation, this is going to stay exactly the same here. Our deuterium is still wedged, and our H is still dashed. So your intermediate A would look exactly like this. And then all of that I was saying before about like how we know it's going to be only one inversion, we kind of see it come together here now. If I invert this stereocenter here at this alpha carbon, I will end up exactly with this right here, the H and deuterium switched. And of course, that's what we know we need. So yeah, this really is like a puzzle, but we can do more examples in class as well. I know me talking at the screen is a little different because I can't stop if you guys have questions. So if anything sounded kind of confusing, again, it's just because we just started this on Monday. But again, it will all come together eventually when we do more practice with it. But again, this would be your molecule A, and then this down here would be your answers for part 1 and 3.